Hello, my name is Addison Thompson and I will be introducing the background of our Feeback Project. Workers in factories and warehouses are constantly faced with the challenge of improving efficiency while upholding rigorous safety standards to prevent injury or loss of or damage to property. To accomplish this goal, workers commonly use heavy cranes to move large loads. The cranes are mounted to the roof of the building, and while they move, workers or product is commonly near the path of the crane. To increase efficiency in the workplace, these cranes need to move as fast as possible. However, the faster they accelerate, the more that the load that the crane is lifting can swing, and that can cause danger to anyone standing near it, which is extremely common. Currently, to better optimize this system, we propose to create a controller that will measure the swinging of this load. It will measure the angle that the load has moved, and it will control the velocity of the crane, so that way it does not swing too far and cause danger to anyone. The way we will measure the success of this project is by the amount of time it takes the system to adjust once an excessive angle is observed, and by by how much the angle exceeds that of what is just determined as safe. If multiple unsafe angles occur, that means that the system is not moving slow enough, and that the factor of safety needs to be adjusted. Our system is comprised of a mass, the length of the crane, and then the angle that the crane is off of 0 degrees. And the input will be a velocity, an x impulse to move the crane. And then our transfer function is dependent on gravity and length due to the fact that mass cancels out of the equation when it is reduced. And this can be seen in the images below. And eventually our transfer function reduces to have 2 poles and no zeros initially.
When analyzing the stability of our open loop system, we found that through the Routh-Hurwitz method, our system was not Bible stable. Also, without any modification, our root locus plot was only on the right-hand plane, which did not allow any of our specifications to be met. Next, our group assumed that our plant would not be disturbed by outside forces. This is because it is an indoor operating crane, and with extra precautions taken by the workers, for example, removing all objects or people out of the way of the crane, it would not be subject to any outside sources. In the design portion of our project, we found that steady-state error, settling time, and percent overshoot were most applicable to our project. Settling time to ensure that the crane would be operable in desired speed, overshoot to ensure that the crane did not sway too much out of range, and steady-state error to ensure that the operators of the crane are not injured during use. To make these specifications possible in our locus plot, we decided to utilize a controller that was not discussed in class. This controller would have to implement 2 new zeros to our system. As you can see with our 2 zeros implemented, our poles lie on the left-hand side in the required region.
Okay, so as Lee was talking about, our open loop root locus for the new 3 zeros, as you can see, we have the design requirements there with the percent overshoot and the settling time. And so the white area shows that our 3 poles are inside the allowable area, so we definitely are able to our transfer function, our new transfer function with the 2 zeros does allow our poles to be inside the area that meets our requirements. And so the next 2 couple of plots show our open loop. We have an open loop Bode diagram that shows our magnitude in dB and then our phase. And the next plot shows the step response of this open loop function. And so Addison talked about 2.1 and 2.2, which was the problem setting and how we were going to model our overhead crane. Lee talked about 2.3 and 2.4, which was analyzing our system, and then 2.4 is making all the requirements and talking about what we would need to do to see if it was stable or not. So I'm going to talk about 2.5 and 2.6, which with 2.5 is verification iteration, and 2.6 is our robustness. So with 2.5, our verification, as you can see, we have our Simulink model right here, and it has our complete closed loop function. So we have our PID with our implementation. Like Ali said, it's kind of out of the scope for what we were doing, and we had to implement the 2 zeros, but there are possible implementations. And then we have our transfer function, and then we have we've closed the loop with just our feedback. And so pretty much just to verify that we actually have stability and whatnot, we looked at a Nyquist plot of our system, and as you can see with our Nyquist plot, we have it's all on the right side, so it doesn't encircle -1. So our n is 0 and our p is 0. So therefore our z would be equal to 0. So we have a stable function, transfer function. And for more verification, we have we ran the Simulink model and plotted the step response timeout. And as you can see, to see if it actually met our requirements, our peak is about 1.25, I'd say. So if we were to do that calculation to get our percent overshoot, it is about 25%, and which is what we were aiming for. And our settling time is a little bit past 1.5, but it is right there. It kind of differs, maybe about like 1.7 or so. But so with that and our after running our Simulink model, we did see that our system does meet the requirements that we wanted, and it does show stability for which we want for our overhead crane system. Okay, so now to talk about 2.6 with the robustness, we are looking for our phase and gain margins, and we look at the Bode plot. So we do not cross -180, so therefore we cannot have a gain margin, and we also do not cross 0, so we cannot have a phase margin. And pretty much we came to the conclusion that because we used a controller that's outside of our scope, we would therefore not have, we would not be for sure if we would have a phase or gain margin. So when we were trying to, with 2.6 asked to find a time delay, we cannot find a time delay just because the only equation that we have is our phase margin is equal to our crossover frequency times that time delay. And since we don't have phase margin, we can't find the time delay. So it's kind of outside of our scope of this class if we were to do some more calculations to find that time delay. But because of the controller that we use, we will not be able to find that time delay with no phase margin.
The goal of this project was to design a system that could accurately model the movement of an industrial crane. The input into this system was the velocity and the amount of sway in the load as the crane accelerated. Our design parameters were to have a settling time below 1.5 seconds and a percent overshoot of less than 25. After adding 2 zeros to our initial transfer function, it was determined that the system was stable and met all design criteria. This was determined by analyzing the Bode, Nyquist, root locust, and step response plots, which were all created using MATLAB, Simulink, and the CISO tool. Additionally, due to the unique constraints of this system, we were unable to determine the amount of additional time delay or controller gains that the system could withstand because that analysis went beyond the scope of what we learned in feedback.
We thank you for listening to our presentation. We hope that that you understand how we would want to describe or model our overhead crane, and we hope that at some point we could be able to actually model this and analyze this, and maybe someday it will actually be useful. Thank you. We thank you for listening to our presentation. We hope that that you understand how we would want to describe or model our overhead crane, and we hope that at some point we could be able to actually model this and analyze this, and maybe someday it will actually be useful. Thank you.